Hello, today I would like to give a short introduction to the basics of the Kotlin Gradle plugin, especially to its fundamental models, which we call TCS, potentially give even a little bit of a history of why TCS exists, why it might be a little bit confusing from time to time, and what are the alternatives we have considered when working on the Kotlin Gradle plugin. In order for us to effectively show how the Kotlin Gradle plugin works, I think it's best to just create a very empty Gradle project, load the multi-platform plugin, as it is a superset of the regular Kotlin JVM plugin, and just see how the entities relate to each other. In order to do this, I am just creating a very simple empty project completely from scratch. I highly recommend being able to set up Gradle projects from scratch, from hand. I know we have great wizards in IntelliJ, as well as we have good wizards in the web. I think KMP wizards in the web are doing a lot of heavy lifting for you, especially when it comes to setting up the entire build for your mobile application, connecting and including Xcode into your project. All of those things are really good. But it is also really valuable being able to just set up the absolute basics for what you need in a simple project and understand what other options and configurations you might not need. So for us to get started, I think we need to just create a settings Gradle KTS file. And the reason for us to set up some global settings is mostly because we would like to set up the dependency resolution management block and the plugin management block. This means we basically just need to tell Gradle, hey, if somebody requests a plugin, here are some repositories that you could look into if you are able to find this plugin. And also if somebody is requesting some dependencies, maybe you can go into other repositories here to look for them. So in order for us to configure Gradle, being able to resolve some dependencies, we basically just need to open the plugin management block and declare the repository. Most of the time, you just need Maven Central. Similar thing can be done for regular dependencies. So we can open the dependency resolution management block, declare the repositories, and also tell Gradle, we are totally happy for the entire build to just use Maven Central. Let's resync this project. And now let's also create a top-level build.gradle.kts file. Now, inside this build.gradle.kts file, I am going to load the Kotlin multi-platform plugin, and I'm going to show the basic models we have in there. In order for us to do this, I'm using the plugins block. I'm loading the Kotlin multi-platform plugin, and I'm requesting the version 2.0.0. K2. So we should now be able in a few seconds to have autocomplete available for us. And we will be able to see that there is now a Kotlin block. This Kotlin block acts as the entry point of configuring all entities related to Kotlin. This is basically the entry point containing all the models. I'm not sure. I think I said exactly this a sentence ago, but in any case, there are different Kotlin blocks. You see that Fleet is providing us with the information that the receiver inside this Kotlin block is a Kotlin multi-platform extension. Inside a Kotlin JVM project, you might see a Kotlin JVM extension. Both of those extensions will inherit from Kotlin project extension, and a lot of the entities will be the same. Now, if I would be just creating a very simple multi-platform project, you might have seen it being done by declaring something like JVM, or you call into Linux x64, Linux ARM64. You might request something about iOS and whatsoever. Let's sync this and try to understand what we're actually doing when we are calling a function like JVM, Linux x64, or Linux ARM64. We can do this by opening the terminal and us invoking a Gradle task. For us to just compile, we can leverage the Gradle W assemble, if I'm typing it correctly, assemble task, and see what it's going to do for us. We will see that now inside the build folder, there are some things already created, but we do not see any real output yet. We can check what is going on by asking Gradle also to include the information, the info logs. So I'm invoking the same task again, providing -I to get the info logs. Now let's see what there is. JVM class, JVM main classes, all of this is mentioning it being up to date. But we also see regularly that there is no source. Compile Kotlin Linux ARM64 has no source, therefore it has nothing to do. Fair enough, I just created this project. I just declared that I have something JVM, I have something Linux x64. There are no sources. So let me just create some source files, invoke the build tasks again, and see what we get out from there. And then finally, we try to understand what we're actually doing if we're calling into this JVM, Linux x64, and other such convenient functions. For multi-platform, you might know that a very simple way of providing sources is just using the common main source folder, and we will get to what this actually means in a few minutes. To do this, I'm creating a common main.kt file inside this src common main Kotlin. Let me provide some source code. Let's clean the terminal, and again call into Gradle w assemble. You can now see that it's actually compiling something, and it takes a little bit of time to do so. So let's look into the build directory and once again investigate what we can see. We now see that, interestingly, there are now new folders that we have not seen previously when not providing any sources. One of the source folders is the classes/Kotlin folder. And in there, there's our targets, and there is something that looks like class files, so meaning we provided some compilation for JVM, but also we have produced a klib file for Linux ARM64, and we have produced a klib file for Linux x64. This is quite nice. So we see that we took our source code, our common main class, and we were able to compile it to a common main.class file and corresponding things for the native world. We see that inside these classes, there is inside this build directory, build classes Kotlin, it mentions JVM, Linux ARM64, Linux x64, similar things, similar names of what we have done here. And I can tell you that those functions here are basically convenient functions to register targets. So this is the first thing when we talk about TCS, meaning targets, compilation, source sets, which is the model the Kotlin Gradle plugin is using. The entry point, this multi-platform extension, can contain multiple targets. We can even see this by going to the targets and see that targets in here is a named domain object collection, which is a type coming from Gradle. And it basically is something that you can observe, you can register new targets, it will create targets, it has factories to create targets. And when you call into such functions, you are basically registering targets inside this Kotlin.targets container. Let's use a debug task that we can execute to just print out some interesting information that we have inside this Kotlin multi-platform extension. In order to do so, let's register a new task. We call it debug. When the task is executed, we can reference the Kotlin extension. We can ask the targets. And for all the targets, for each, we will print the name of it. Target.name. Let's invoke our debug task. We now see there are the following targets registered. The JVM target, that's not so surprising, as we told Kotlin that we kind of like to have a JVM target. We see Linux ARM64, also not too surprising. We also see Linux x64. Again, we declared that. Interestingly enough, we also see a metadata target, and I'm going to cover metadata in potentially upcoming recordings. Now, this means that Kotlin knows about certain targets, and those targets can somehow be compiled. But how do those compilations work? And how does this work, for example, with tests? As we've seen, there's JVM main. We do not see anything regarding tests. In order for us to understand how Kotlin actually compiles something, we need to understand how targets relate to compilations. And this is quite simple. Each target has a set of compilations that it owns. So we can try this out by printing all the compilations that exist inside the JVM target. Let's do this by, again, using our debug task. We can retrieve the JVM target, minor node, just calling this JVM extension function or like utility convenience function will basically perform a get or create. Calling it a second time will just return you the previously created target. So you do not end up creating multiple JVM targets. You can just reference the JVM target using Kotlin.jvm parentheses, calling it to this function once again. So we see that all of those targets, they have a set of compilations. If you look at this, it's again a domain, no documentation available, but it should be, can look into it. It's again a named domain object container, basically similar to how the Kotlin multi-platform extension contains multiple targets. Each target has a set of compilations. Now let's just print them. So for each of those, let's print the compilation and its name. Let's execute the debug task. By the way, I'm using an alias, Gradle W's alias to GW. I'm just saving my time myself some little time. So let's invoke this debug task. And we see that there is a main compilation and a test compilation here by default. This means that calling into such a utility function, a convenience function, it sets up a target and also provides some conventions. One of the conventions being that there is a main and there is a test compilation set up for you by default. The only exception to this rule basically is the Android target. Compilations and Android are a little bit more difficult because they might have build flavors and they might have build types or build flavors. Let's not get into this right now. For regular Kotlin targets, we will get away with just having by default a main and a test compilation. Let's now look on how we could actually also compile something for the tests. Let's therefore just invoke the check task and see if it does any compilation. Again, we do not see something interesting in the build directory, so let's use -i to see what's going on. And we again see a lot of no sources that are provided. Not too surprising, we have not written any source code for tests. Let's provide some source code for tests and see how it affects us building this project. For us to do this, I will create a new file. It's under src, common test, Kotlin, and of course, I do not want to have a Kotlin here. I want to have a Kotlin common test.kt. Let's provide a simple common test class. Now let's clear the terminal and again provide the check task or invoke the check task. We see now it takes a little bit of time. It's linking the debug tests for Linux x64. So it's doing something. The build is successful. Now let's investigate what's there in the build directory. Now we see very nice that under the JVM folder, we now see that there are classes for main and there are classes for test. Yoo-hoo, we see we compiled also common test to class files. Looking into Linux x64, we see that we were able to provide a demo test scaleb. However, we have not compiled a demo test scaleb for Linux x64. Maybe this, we have not been able to provide the scaleb for Linux ARM64. Let's not get into detail why that is, but so far we understood that we have the ability to just use a test and a main compilation that they are created by default for us once we registered a target using this convenient functions. How does this Kotlin Gradle plugin now figure out which sources it actually needs to compile in which compilation? This brings us to the concept of source sets. Now, source sets are the container or like the rules of what source code, which physical source file it should actually compile in a compilation. Now, let's reiterate. The Kotlin multi-platform extension contains a set of targets. Each target contains a set of compilations. Those compilations might be a different type. The compilations that come from the JVM, they are Kotlin JVM compilations. They do compile, they invoke the Kotlin compiler in a way that it actually tells it that we care about producing class files. A Linux x64 target contains also compilations, a set of compilations, and all of those compilations will be of the type Linux x64 native compilations, and they will invoke again the compiler in a way that it produces something for the native world. How does this relate to source sets? The simple answer is that whilst every multi-platform or every Kotlin project extension contains a set of targets, and each set contains each target contains compilation. Also, each compilation owns or contains a set of sources. However, the source sets are also available top level. And this brings us to a block that you have probably been seeing whenever you have tried to work with any Kotlin multi-platform project. You see that the source sets concept is top level available, and you will be able to configure some of the pre-existing source sets using a convention that the Kotlin Gradle plugin provides. This here is hard-coded in the Kotlin Gradle plugin. It knows that there will be source sets that are called common main. It will know that it will create, it will also know that there is a source set called common test. However, you also are able to configure source sets and use source sets that might be Apple main. And what the Kotlin Gradle plugin does for you is that it basically provides this as conventions to you. You are free to use them. They might get set up, they might get created, and they might belong to whatever you think they might belong. Okay, this sounds confusing, but looking into compilations, they will contain a set of sources. Let's look into the main compilation of the JVM target and see what source sets it contains. Therefore, we ask for the compilations. We saw previously that there will be a main compilation, so let's request the main compilation of the JVM target. Now, if we have this compilation, we can ask for Kotlin source sets. And for each of those Kotlin source sets, let's print the name of it. Invoking the Gradle W debug task reveals that the JVM, the main compilation of the JVM target, has a source set called JVM main, which also, interestingly enough, can be accessed here by the source sets.jvm main convenience function, or accessor, as we call it. This is also done by the Kotlin Gradle plugin as a convention. If I would like to add additional compilation, let's do this by using JVM compilations create foo. We should now be able to see that there is a source set created that is created by using the following convention. It will use the name of the target as a prefix and the name of the compilation as a suffix to create automatically a source set for you. Let's print the source set by asking the JVM compilation here to get us the newly created foo compilation. And we will still now print all of the names of the source sets that are associated with the foo compilation. executing Gradle wdebug reveals that indeed the source set is created and it follows the convention I've just described. JVM being the name of the target. We also can, by the way, ask Kotlin to give us the target by name. So if we do this, get by name, and ask for something called JVM, and we then ask the JVM target about its foo compilation, we will still see that foo debug will be printed. Let's try it out. I was right. This means that when we call into such a function, JVM, it will get or create this JVM target. If it's absent, it will also make sure that by convention, it creates the main compilation, it creates a test compilation, and for each of those compilations, it will make sure that there is the corresponding source set created for you automatically. Now, why is the source sets here available on the top level? And I think one of the reasons is because DSLs are just really, really hard. If you would want to configure your source sets, and you would be required to resolve like the compilation by name and then request the source set by name, it will basically be a lot harder than you just being able to access the source set here, common main, and configure its dependencies. Now, this brings us also to one of the interesting parts about Kotlin source sets. You see, whilst I was able to compile for JVM, I have not used any sources that are located in this JVM main/Kotlin source directory, which again is basically the convention. If I have a source set in Kotlin that is called JVM main, the location by default of the source files are expected to be in src JVM main/Kotlin. You can change that, you can reconfigure this, but this is just the basic default convention. Right now, we, however, just have the sources directly in common main Kotlin. Still, we were able to compile this common main into JVM bytecode and something for native. This also brings us to the reason why source sets are somewhat special. Right now, targets and compilations are nicely following like a clear ownership model. The targets belong to the Kotlin extension. Like a Kotlin extension has a set of targets. The set of targets, or every target has a set of compilations, and this compilation only belongs to this one target. So there is no mix and matching. However, you can see this common main, however, is available for us to compile for the JVM, but we are also free to compile it to Linux x64 or Linux ARM64. Which means this does not really belong to any of the targets directly, but it somehow is included. How does this work? Let's again use our debug task, make it a little bit simpler by requesting the JVM target like this again. We request the compilations, we ask for the main one, and we again print all the Kotlin source sets. We see it just prints JVM main. But how does this JVM main get this common main KT file being compiled for the JVM? There's another way of accessing the Kotlin source sets that are contained within a compilation, and it's all Kotlin source sets. I'll cover it in a second, but let's just try what this will give us if we execute this debug task. Oh, very interesting. We see JVM main and common main are listed if I ask for all the Kotlin source sets that participate in this compilation. Similar thing would happen if I'm asking for the Linux x64 main compilation. So what I'm expecting to see right now is that instead of JVM main, we will see the Linux x64 main, and we will still see common main being listed as all the source sets that participate in this compilation. Oh, interesting. We see Linux x64 main is available as I have predicted. We see common main being available as predicted, but we also see that, again, by convention, the Kotlin Gradle plugin includes more source sets. It automatically includes Linux main, but it also includes native main. So you are able to just put code in Linux main if you just want to share this code for Linux-based targets, you can put specific code in native main if you just want this code to be available for all native targets, or you can write code inside common main if this code should be available in all of your targets. This is done by a convention in the Kotlin Gradle plugin. You can reconfigure those conventions, and I can share further recordings how this can be done later. But so far, it's the easiest to just stick with the conventions, and most of the time you will just be happy using some of those predefined source sets. How does this source set end up inside these compilations? There is a mechanism on how to connect the source sets, and using this mechanism by hand is highly discouraged. I want to share that we have worked on this API, which is called depends on. We have published this as very early on, as very early versions of Kotlin multi-platform, and we have seen that it is highly confusing, and it can produce projects that are extremely convoluted and will break the Kotlin compiler at some point. However, I can show it quickly on how this is done under the hood, just for us to get some understanding. So let's write some code that the Kotlin Gradle plugin also executes in order for us to understand how it connects those source sets. Let's say we are the Kotlin Gradle plugin. We just registered the JVM target. So let's have the target available here. We then have this compilation created. So let's create a compilation by referencing it. Or let's get the compilation by asking compilations get by name. We know that there will be a main compilation. So this main compilation will, by default, every time you create a compilation, it will always create a corresponding source set alongside with it. There cannot be a compilation that does not have a single source set associated with it. There are some projects that will use multiple source sets directly included in a single compilation, but this is highly discouraged. I remember even that we deprecated this. So let's ask for the source set that is associated with the main compilation. There's a way to do this. We can ask for the default Kotlin source set or default source set here. This will mostly just follow the following convention. Again, creating a source set if absent that follows name of the target as a prefix, name of the compilation as a suffix. In this case, JVM is the name of the target, main is the name of the compilation. Therefore, I expect a source set that is called JVM main. We can call it this way, JVM main. Now, how does JVM main get anything from common main? It's quite simple. There's an API called JVM main, depends on common main. We can ask the source set. For the sake of making it simple, we just get the source set that is created by default from the Kotlin Gradle plugin called common main. And we can say JVM main depends on common main. And what this does, this is a very low level API. Please do not try to use it. There are a lot of intricacies. There are a lot of strange things that go on if you call depends on, and if you do not get it right, you probably will be able to compile your project on the CLI, but the IDE tooling gets completely crazy. So we found that abusing this API is not a good idea, at least not if you want to keep sane tooling. However, what this does is it connects those two source sets, and it will allow that when the compilation asks for all source sets involved, it will follow this chain of depends on calls and find this closure of all source sets that are really involved. Also, when some dependencies are resolved, it will include all the dependencies that are declared in the common or in the upper source set. So if you declare depends on another source set and you declare dependencies on this source set, it will include this to the target. Now we can see source sets are a little bit strange. It's called target compilation source sets, TCS, and this follows a nice pattern for targets and compilations. However, the source sets are a little bit tricky because they have this low-level mechanism of depends on. It's not necessarily too clear on how to configure them. So I assume that most people will just have the best time if they just use the conventions created by the Kotlin Gradle plugin by letting it just set up default source sets that can be used and can be discovered, and where you can just put your code in and be happy. I think that's it for a short overview of how the Kotlin Gradle plugins model works. I will potentially consider creating more in-depth recordings, explaining more in-depth on how to do certain things with the Kotlin Gradle plugin. For now, I just think it is enough for one recording. And as a bonus, I would like to also explain some bit of history. This TCS model obviously is not the most beautiful when it comes to Kotlin multi-platform, especially the part with source sets make it a little bit hard to understand and a little bit hard to get a good mental model on how things are actually connected, where sources are included in which compilations, and what this all means. The reason for this is that this TCS model was the initial model before even Kotlin multi-platform was implemented in a single project like this. Therefore, we just reused and kind of retrofitted this model to fit multi-platform, even though it was not perfectly fitting. We tried to reimagine and re-implement and re-architect a new model, which we back then called KPM, which stands for the Kotlin Project Model. But redesigning such a model is extremely complicated, just covering all of the different use cases, coming up with a transition model, with a smooth transition for existing projects to the new project model is really, really hard. And especially DSLs, they are really, really hard. We gave up on KPM for now. We stabilized Kotlin multi-platform with the existing TCS model because it was mature enough and we were able to provide good tooling for it. Amper and other build systems are now experimenting with learnings as well that we had from this KPM design approach. And I think that a lot of simplifications can be done here. And I'm quite looking happily into the future, working and showing how Amper works in upcoming recordings. I think that's it for now. Bye bye.